Well, I have 2 o'clock on my watch, so I'm going to go ahead and get started. There may be a few people that pop in over the next few minutes, but it looks like we already have a pretty good crowd today. So there's a few people that I can see. If you give me a thumbs up, if you can hear me okay. Does that work? Okay, good. I will assume everybody that I can't see is also holding their thumbs up. I'm Steve Schrock. I'm a professor in the Civil, Environmental, and Architectural Engineering Department at the University of Kansas, and I'm also the director of the KU Transportation Center, and I'm also the associate director, one of the associate directors of the Mid-America Transportation Center. So it's my pleasure today to be the master of ceremonies for this talk. I'd like to introduce Dr. Chris Depcik, who's one of our mechanical engineering professors at KU. I'll just say a little bit about Chris. He's been in his department since 2008. And during that time, he has focused on sustainable energy usage and transportation infrastructure, which is going to be part of what he's going to talk about today with his cost-effective LiDAR treatments. Chris has also been the faculty chair for what's known as the EcoHawks student design group on campus. And it's a group that researches and builds electrified vehicles and renewable energy using renewable energy sources, including interconnected vehicles with energy sources. So it's been kind of an interesting group to watch. In another talk, he should tell you about the time they completely retrofitted a Volkswagen Beetle into an all-electric car, which is sort of a neat thing to have on campus. Chris is a member of the American Society of Mechanical Engineers and the Society of Automotive Engineers. In 2011, he received one of our highest teaching awards at KU, which is a W.T. Kemper Fellowship for Teaching Excellence. And he's also received the Society of Automotive Engineers Ralph R. Teeter Educational Award in recognition of his transportation-related research and educational activities. So Chris is a rock star in our school, and we're glad to have him. Today, he's going to talk about his MATSE research project entitled Design and Testing of Cost-Effective LiDAR Systems for Transportation. So that is just really briefly how it ties into the Mid-America Transportation Center. That use of LiDAR systems really is about, obviously it's about low cost and high density data collection that can be used for the US DOT's Highway Performance Monitoring System reports. So it can get things like traffic information on roadway delays, accident crash investigations, risk mapping, pavement quality monitoring, and a host of other things. What Chris is talking about today, I don't want to steal his thunder, but he's really talking about how can you miniaturize that treatment so it can be used in a wide variety of transportation applications. So, Chris, with that, go ahead. If anybody has any questions, I see everybody is muted, I believe. If you're not, please remember to mute yourself. If you have any questions, feel free to write them in the group chat on the right, and then I will keep a catalog of those, and when we get to the end, we'll go through the question and answer phase. Chris, please.
Great. Thank you, Steve, for that introduction. I'm, not that put enough pressure on me there, calling me a rock star and everything. So that'd be great. But I'm happy to present today. Thank you for all showing up this afternoon. And in fact, I'm going to be presenting today with my graduate student, Ms. Devin Mittman. She's going to be taking the bulk of the presentation today because she's the one who actually does all the work. I just take credit for it. So I think it's always good to see the people who actually do the work, and she'll be able to answer a number of very insightful questions that I'm sure you'll have. So today we'll be talking about the design and testing of cost-effective LiDAR systems for transportation. Hopefully everyone can see my slides just fine. So a little bit about the outline of the system, outline of the talk today. I'm going to start off by talking a little bit about the original motivation behind the work and how it's morphed to talk more about safety overall. And that leads into the goals that we developed here. And those goals lead into the development of two LiDAR systems. One's a two-dimensional one, and one's a three-dimensional one. And that's where Devin will take over. She knows the systems in intimate detail and will be able to describe how they function and also the results that we've generated. So she'll take the results in discussion and then conclude with our findings to date. And then we must acknowledge those who have sponsored this work. So the original motivation really resolved around bicyclist safety. Because of highly variable speeds, road surfaces, live traffic, bicyclists have a number of safety concerns. And specifically, you consider the blind spots and also a potentially inadequate road infrastructure. So here on the right, you see the illustration of a bike where it's basically using a mirror to help indicate, some rear-facing awareness. But these mirrors are somewhat limited and offer kind of poor depth perception. In addition, we see on the right, this is where road conditions really can play a role if you're not aware of a pothole and if the road infrastructure isn't necessarily where we want it to be. And this can result in a significant number of injuries. And we see those with respect to bicyclists regarding basically being hit by the car is about 29% of all bicyclist injuries. And then also these road conditions actually account for 13%. I'm not sure everyone's really aware of how prevalent these road conditions can play in bicyclist safety. Now, as Steve mentioned, part of the EcoHawks work that we've done is actually design and build electric bikes. We see this really as being part of the infrastructure in personal transportation in the future. These electric bikes or e-bikes can even pose a greater danger for the riders because they're quiet, they're fairly quiet, they're faster, you can go up to 30 miles per hour, even more, and they're also significantly heavier. So there's a lot of potential more damage. So what we really would like to see is kind of a rear-mounted system that could provide essentially early warning for traffic and potentially map the road surface or give us some indication of the road surface along the way. Now, in deference of using radar, we decided to go with LineArm. And so it's very similar to radar, but it can provide a greater fidelity. If you're not familiar with LineArm, what it does is it uses near visible light waves to essentially identify the distance the object is from a sensor. So on the right here, you see a LiDAR rangefinder. And what it does is it transmits the light in one basically optic source, and then it hits off the object, and then it measures the time it takes through that receiver that the object is essentially away from this rangefinder. So you can do a very simple calculation to get the distance the object is away from the rangefinder. And so what this can do is it can generate a very high fidelity distance measurement, and it can be used to generate detailed maps of surroundings to essentially warn of dangers. So this allows for high speed and accurate monitoring potentially of traffic surfaces with low essentially computational requirements, maybe for data processing there. But it is going to require a rotation and coordinate data processing. So the LiDAR can provide, a single data point, but if you rotate it, then you can provide, a two-dimensional sweep or a three-dimensional sweep. Our original efforts back in 2017 and into 2018, we decided, okay, for a bicyclist, what would we want to do is essentially identify the vehicle and then how far away a vehicle would be from the rear of the bicycle. And so we did some experiments. We built the system on the right where we have a Garmin LiDAR Lite rangefinder that's mounted to a stepper motor, and then we used a Raspberry Pi cam essentially to identify the vehicle. So we use an OpenCV software environment to essentially train that to identify vehicles and then ideally link it up with LiDAR to indicate that vehicle distance away. And we had some limited success with this in that the OpenCV software essentially identified a good number of vehicles, but it missed a number of them, and it actually erroneously identified things like light posts as vehicles. So, further training was required. But perhaps what was even, more problematic was the interface between the camera and the LiDAR with respect to identifying the vehicle and at the same time indicating via LiDAR how far away that vehicle was. And then we looked at the processing and rotational speeds, and they were just too slow for this small system that could be mounted in the back of a bike. It took about 2.45 seconds, essentially, to sweep about 75 degrees. And as you can imagine, for a car moving fast, that's essentially too slow. So while we accomplished some objectives and we kept the cost moderate for original efforts, we decided to go back to essentially the drawing board and think about what could we do that was more ideal. Along the way, we continued to look into the research, and we found that when we researched these databases, the Transportation Research Information Systems and the Research in Progress database, we found LiDAR extensively mentioned for a number of different transportation research activities, such as lane width estimation, traffic data intersections. but essentially all of them employed commercial hardware that was about $6,000 to $100,000. And so there were very few of these transportation projects that used essentially low cost and inexpensive LiDAR systems. Here on the right is an illustration of research at the University of Arkansas, where they set up 2 LiDAR rangefinders to essentially measure the signature of a truck as it passed by. And so they had good success doing that, and the costs were moderate. But what was interesting is that when we're looking through this research, found this nice, pulled this quote out of this abstract from the Kentucky Transportation Center project that indicated the expense of data collection and post-processing might actually outweigh the overall benefits for a LiDAR system. So we had some limited success with a non-commercial system. We were able to keep the costs moderate, and we started thinking about what would be needed in a transportation environment that could really help out from a safety perspective. So we saw this as essentially the need for a low cost and accurate system that can provide this, again, widespread implementation. So we came to 2 goals. So let's build 2 systems based on our knowledge of what we've learned before with our original 2-dimensional system. Let's revise it. Let's improve its rotational speed. And then let's just use LiDAR to see if we can identify objects in distance, and at the same time provide a warning system to the rider. So can we identify objects at a relatively fast rate and then provide a warning system to the rider? Our second goal was to say, okay, let's see what a low cost, essentially technology on the cheap 3-dimensional LiDAR system can develop. Can it do an accurate mapping of surroundings? And then can we use it to identify things like potholes and road hazards? So that kind of leads into our 2 systems that Devin has worked on. And so with that, I'm going to turn it over to Devin to essentially chat about the 2-dimensional and 3-dimensional systems.
So first, we developed a 2-dimensional LiDAR system. So if we just move on to the next slide, we can see how that system actually works. It used a Evo 6-meter LiDAR system, or LiDAR sensor, which has a distance range of 15 meters.
Devin, can I stop you for just a second?
Yeah.
Is it possible you can find the microphone and speak a little more into it? You sound a little muffled, and I want to make sure people can hear you.
Okay, maybe I don't have a microphone, so I'm just on a laptop.
Okay.
If I move closer, does that help?
It can't hurt. So.
Okay. So, like I was saying, the system as a whole, as you can see in the first photo, is encased in a 3D printed housing unit that has a removable front door so that I could easily access the circuitry inside of it, make adjustments as needed. It's fully enclosed so that during testing, water, dirt, whatever wouldn't get in and mess with the circuitry. It has a 5-volt bipolar motor. It's a stepper motor, which means that I can control exactly which angle it turns the motor, turns the sensor at. It's run entirely through the Arduino Mega microprocessor. It uses a single on-off switch for easy use, which is the switch. It starts collecting data, everything. It also saves the data to a micro SD card inside and run entirely through a 9-volt battery. As we move on next, we can see how all of the circuitry is connected. Like I said, the Arduino runs the SD card, runs the LiDAR camera, runs the bipolar motor, which has a minimum turn angle of 1.8 degrees. Eventually, I connected 3 LED, essentially blind spot alerts for the device rider. One that would alert the rider to an obstacle in the left, center, or right lane the LiDAR was facing. It's capable of real-time data processing, so the system would be able to alert the rider in real time if an obstacle is behind them, if a car is coming up behind them. And after data collection, a MATLAB code is able to convert all the data saved to the SD card to visual graphs to be able to show what the LiDAR was looking at and whether or not it successfully turned on the appropriate LED. The entire system costs just about $250 minus the 3D materials, so printing. And next, we have the results of preliminary stationary testing, where I would just hold the system still and map essentially what is the stationary cost. So this first test was in a parking lot. It took about half a second for the system to sweep 100 degrees, 50 degrees on either side of straight ahead. The LiDAR was held 2 feet above the ground so that the system would be pointing mostly at car bumpers rather than the hood or the larger windshield, which wouldn't reflect directly at the LiDAR sensor. The theory was that the bumpers would have the best chance of creating solid data points. Unfortunately, because it was just LiDAR, you can only tell how far something is away. It's unable to determine exactly what the object is pointing at is. But by using a corresponding visual photo there of what the data is looking at, I was able to identify gray car and silver car appropriately as opposed to the building in front of them. Some changes were made to the code after this so that any group of data points would be labeled as a car if they were stationary and close to the bike or nearing the bike. So for mobile testing, I doubled the step angle from 1.8 to 2.6. That way the system would be able to turn faster to the whole 100 degrees in half the time roughly. But this did lead to a single car would then result in fewer data points. This is the point where I added the LEDs to the system so they would just connect to the LiDAR that was positioned on a bracket on the back of an electric bike, roughly about rear wheel height. Again, pointing at the bumpers of cars. And the LEDs were attached to the front handlebars. So you can see from the first photo I have of the testing. We have a red Jeep that was reversing out of the parking spot, fairly slow speed, but it did successfully trigger the LiDAR system. You can see that it only collected 2 data points on the car, even though it was moving slowly. Because it was still moving, the LiDAR system did not pick up as many data points. And you can see from the second photo, the silver minivan, because it's stationary, is a large surface, you're still able to collect many more data points and successfully trigger the correct blind spot LED alert. It's determined that any car moving roughly under 15 miles per hour would trigger the correct LED to turn on. Anything over 15 or even 18 would be able to pass through the field of view though without the LiDAR potentially detecting the vehicle. Let's move on. Controls of the system as a whole, it was very small, it was lightweight, it was portable, easy to use, with on-off switch and model the data. It accurately detected stationary vehicles and vehicles that were closing in on the LiDAR system. Any vehicle that was moving away or something that was farther than about 25 meters away, the LiDAR system ignored. There were some issues though, especially during mobile testing. Due to the nature of riding on a bike, when the bike would turn and lean, the LiDAR system would detect the ground and falsely say that that was an obstacle to be avoided, just the ground. Additionally, when the bike turns sharply, it would be able to detect a stationary vehicle maybe in 2 different positions, neither of which would be accurate then to where the bike is currently headed. So some significant algorithm development would be required, something that could sort through all of this data and maybe something that would monitor the position of the bike, the speed of the bike, or any leaning to the system to be able to account for these false positives. So moving on to the 3-dimensional LiDAR system. An undergraduate team developed the first version of the 3D system using a Garmin LiDAR Lite DC rangefinder. It's about the same size as the Caribou. It has a 40-meter range as opposed to a 15-meter range, but it still works fine. Used a 5-volt stepper motor and corresponding motor controllers. So one motor would be positioned horizontally, and then a second one would be mounted on top of that motor to turn the LiDAR sensor vertically. All of this is held together with more 3D printed housing, and it needed to be connected to a 5-volt power supply and laptop to be able to be powered and store data properly. So from this next slide, we can see that the connection between the LiDAR and the microprocessor did require a capacitor. That's not that much of an issue. The stepper motors did have a much finer step angle than the previous system. These turned at 0.08 degrees per step. So you could very finely control where the LiDAR camera was pointing to be able to get very dense data sets. The code that was programmed for this controlled the electromagnetic intercept motors directly. The power supply from the laptop was also used to collect the data in a serial monitoring program. And once the data was collected, a MATLAB code was written so that it could create an XYZ Cartesian data cloud from the angle of both motors and the distance of the LiDAR sensor. The entire system cost less than $300, so we're still talking very cheap compared to some other commercial systems. So from initial results, the team was able to get over 15,000 data points, which is respectable. There were some issues though with the motors turning too much. So some new changes were made to the code so that they can more finely control the motors. As you can see from the photo of where they stand, they had set 3 chairs on top of the desk to verify if the model was detailed enough. And as you can see from the resulting point cloud model from the LiDAR system, you cannot tell that there are chairs. You can get the shape of the room, but that's about it. So after they made the changes to the motor, they were able to get almost 50 times as many data points. So they had 7,000 data points. It took them a little over 2 hours to collect that much data. But from the model, you can now see clearly the 3 chairs situated on the desk. Unfortunately, the number of data points meant that they had to use a new serial monitoring program rather than the Arduino because it did not have enough memory to hold 17,000 data points. So from the next part that they did, they sorted out how to separate foreground data points from background data points. They were able to model objects rather than spaces. This meant that they could model, you can see on the left, an engine test cell, and then the corresponding model below it, and on the right we have a race car and corresponding model, neither of which show the walls or the floors surrounding it or view the windows behind them. Next, we have videos of both the original system, 3D system, and then a new updated system. You can see from the first video that the motors are controlled by motor controller board. You can see that the horizontal motor turns first, and then when it reaches the end, the vertical motor will turn slightly. You can see its connection to both the laptop and the 5-volt power supply, meaning that it did have to be connected to a wall outlet somewhere. This limited its portability and mobility. The second video we have is of the updated system. It uses almost all the same hardware, just adapted to be portable, self-powered, and stored its own data. You can see that it's much smaller, more self-contained. It's roughly the size of your hand. All of which fits on 3 circuit boards stacked on top of each other. No motor controllers necessary. We move on to the next slide. We'll get a better look at the updated system. This one uses, like I said before, self-powered supply. You have a 5-volt battery pack and a 9-volt battery pack. The 9-volt powers the Arduino, the 5-volt powers the 2 stepper motors separately. whole thing weighs only about 1.5 pounds and uses just 10 AA batteries to power the whole system. Because of the Arduino's limited processing power, we're only able to collect about 35 samples per second, as opposed to commercial systems which are able to collect thousands of data points per second. But this is a good position to start from for a 3D system, I think. Additionally, the whole system without 3D printed components costs about $220. If we move on to the next slide, we can see the testing done from the updated system. This is done with a pothole out in the parking lot. It's a fairly big pothole, if I do say so. You can see a foot scale reference in the photo to show you the size. It is best to model a pothole I found with the system as vertically above the pothole as possible to get a direct line of sight. The system was also set to collect the highest density point cloud possible, so all of the motors were turning as small increments as possible. It did take about an hour to scan over just over 125,000 data points. And as you can see from the model, you can clearly identify at least the outside of the pothole from where it changes dramatically from red to yellow. And you can see the depth of the pothole shown by the darker blues in the center. To move on to the discussion, we're able to successfully collect over 700,000 data points in a 3D point cloud model. However, in both systems, because they were run on Arduino microprocessing power, which, if I remember correctly, has about a 16 megahertz timer on it, both of them are too slow for mobile applications. They take over an hour to collect a point cloud. By incorporating more powerful microprocessors, though, we'd be able to speed up that data collection time, get more data, and facilitate more inexpensive testing capabilities, whatever they might be used for. Additionally, by increasing the image processing power, could improve accuracy if you equate the sampling rate with the orientation of the system as a whole. And finally, we were able to decide that LiDAR does have the ability to safely influence transportation by allowing a bike rider to use blind spot detection to map roads more detailed, and anything else that a transportation might use. Current LiDAR commercial systems on the lowest possible side were $6,000. These were only a couple hundred. So they'd be easy to use for widespread implementation. The potential exists for 2D LiDAR systems, but you would need further algorithm development to be able to determine which set of data points is a vehicle, which set of data points is a pedestrian, or a sign, or a bush, or any other obstacle that the system might encounter. A 3D system would be good for point cloud accuracy, so long as maybe the processing power, like I said before, is increased. These costs could be relatively low, but any upgrades to processing power would improve speed, robustness, accuracy, and all of these systems have potential for dozens of uses, many of which are not successful. These would be suitable for any requirements of the DOT. And finally, we'd like to acknowledge the Mid-America Transportation Center for their help funding this research, and the U.S. Department of Transportation's University Transportation Center's program for all their support. It's very welcome. Thank you. Are there any questions?
Okay, well, I'll give everybody a few minutes to decide if they want to add some questions in. You can certainly either unmute, or if you'd rather type them into the group chat, you can do that. I have a few questions for you while we're waiting for other people. I was fascinated by the 2D LiDAR approach, and I can completely get the limitations you talked about in terms of, if the bike was to lean over, that you might get some false positives and things like that. My question would be, I think you said that that you increased the range between readings to 3.6 degrees. Is that right?
I doubled the stepper angle from the minimum 1.8. Yeah.
Did you consider in your research at what point at 3.6 degrees between readings that you actually that a car could fit in between those readings, which would give you
Yes,
sort of.
I had about 2 pages of math worked out to figure out if the car was going about 40 miles an hour faster than the bike, what limited time would we have? So I did figure out the critical distance would be about 25 meters for a good set of alert time. And I did figure that 3.6 was the maximum step ankle I could get away with, where I'd be able to determine that a single car would be triggered twice, or at the very least once, if it was going about 20 miles an hour faster than the bike. This is roughly what the results show. However, because of Scott's account for the time spent processing the data of the Arduino, so there is just a couple milliseconds between each data point that it is storing the data onto the SD card. Therefore, the speed of the car dropped down from about 20 miles an hour to 15. To answer your question, if I had increased the angle anymore, so many cars would be able to pass through without being seen.
Mm-hmm. Yeah, absolutely. It seems to me that it's there's a lot of trade-offs in what you'd have to try and figure out on the research side. If you want to squeeze that down so that you have a longer, I don't know what you call that, safety threshold where a car wouldn't be able to hide from your reading, then it would take longer for it to do a sweep across. So then there's a delay in even noticing it. So some of that, I guess, would be overcome in maybe with future processing speed increases and things like that. But it is sort of an interesting, almost a catch-22 when you're trying to design that. If you want to speed up one direction of search, you're making it harder in other ways.
Yes, I noticed that when I was programming, because we're saving the data to an SD card, that step alone, and that line of code takes about 4 times as long to run as a typical line of code, where it's just programming this, can you do this thing? So if in practical use you didn't need to save the data, theoretically the system would run a hair faster.
Interesting.
It's all about what are you willing to give up to make this system run faster.
Yeah, as soon as you test the system, you change the system.
Mm-hmm.
The other question I had was, I guess it was just more of a thought as I was trying to, in my own mind, say, well, how would I design a 2-dimensional lidar that would fit on a bicycle? Is there, and I know nothing about what it costs or how hard it would be to put on there, but I'm imagining some gyros or something you could put on there to stabilize it so that when you went around a corner, the lidar itself would stay level. What does that do in terms of cost? Are those relatively expensive or energy consuming?
I was not thinking about a gyroscope when I was considering how you would solve that problem. I was considering an accelerometer, 3D accelerometer, so it would be able to tell how far it's tilted to one side, just by using the measurement of gravity. And then hopefully it would be able to account that in the tilt rather than having to try to keep the whole system level.
Mm-hmm.
So if the bike had tilted past like 10 degrees and it saw something very close on the edge, it would be like, that's the ground, and then ignore that.
No, and that makes sense too. Then it's something you could program into, as opposed to just depending on it to always be level. That's a good thought.
Yeah. And I know, well, I'm hoping accelerometers are fairly cheap. They're small. I can imagine they cost more than about $20. But I don't know exactly the numbers.
And the last question that I have that I thought of while you were doing this is, I imagine, I think Dr. Depcik mentioned that the speed of the bicycle may be up to 30 miles an hour. So we're not talking about a fast vehicle, but does the speed of the vehicle make any difference did you have to include that in any of your calculations to account for any of these differences? Or
I was also worried about
else?
I was trying to account for the difference in speed from the bike to the vehicle. And I'm kind of a chicken when it comes to riding the bike, so I didn't get up to 30 miles an hour. I was keeping it fairly slow around the parking lot. Um, so I wouldn't be able to answer at super high speed what is the system going to do. But I do know that the TV system that I built was fairly fragile. If I was to adapt it again, I would probably do something much more similar to my previous system, but just remove that second motor. So it's more compact, more stabilized, and it's connected more
Sure.
solidly.
And I think that what was the weight between, or the weight of these two different systems?
They were both maybe 1.5, 2 pounds.
Okay.
Very small, fit in your hand.
Yeah. Relatively light relative to the weight of a bicycle. Okay. Unless you're Lance Armstrong or somebody, you may not notice that 2 pound difference.
Yeah, it shouldn't affect the rider's capability at all.
Well, my capabilities on a bicycle are quite low, so it's every little bit helps with me. Well, I still see no questions in the group chat. Are there other questions anybody would like to ask Dr. Depcik or Devin while we've got them here?
That, or Devin did a good job presenting, so there are no questions and everything was clear.
That's generally what I always assume. If there are no questions, it's because you knocked it out of the park and there's just nothing to ask. So, okay, well, we have one question. Ernest Tufor from University of Nebraska. Hi, Ernest. Hope you're doing well. He asked a question that said, one main issue of using Raspberry Pi is the power source. How is this managed? And did the AA batteries work well?
Well, I actually looked into the difference between Raspberry Pi and Arduino because I had never worked with Arduino before. I know it was an easier learning curve than Raspberry Pi, so I used Arduino versus Raspberry Pi.
Okay.
And with my 3D system, I did have issues with my power supply because I thought I could power everything through the Arduino using only a 9-volt battery pack. The issue being that the Arduino was not able to supply the amount of power the motors needed. That was why I had to add a second 5-volt battery supply. But once I figured out that issue, now there was no problem with using just AA batteries. Through all the testing I've used so far, I haven't had to trade out any of the batteries.
I think Devin hit it on the head there with regards to, we went through it and she was having a problem with the Arduino, and it would be the same thing with the Raspberry Pi, I'm assuming. I don't think there's enough power in those devices to power everything we need. So if you split up the power supply like she did to make sure, well, I'm powering the Arduino, the Raspberry Pi this way, but I'm powering maybe the motors this way, then you don't have any problems with the power supply.
I believe the specific issue with it was that the Arduino could technically supply 5-volt to the motors, but it couldn't supply the amount of current that the motors needed. That was why I had to add the new 5-volt batteries.
So you had separate power supplies for the different components then?
Yes, and that was why I had a double pole, single throw switch.
Okay.
They would turn both, they would connect both power supplies at the same time.
I want everyone to keep in mind she's a mechanical engineering student too. So a lot of electrical engineering went into this.
Well, I can't even understand what that figure says on that screen. It's been too long since I've had an electrical engineering class. So, okay, we have a second question from Billy Connor. It says, my iPad Pro has a LiDAR camera in it. These cameras are rapidly getting smaller. What do you see coming in the future?
I'll answer that one. You're absolutely correct. The LiDAR system that we used here, this Garmin it was the low-powered one. They have a high-powered one. I think it was $140. And you're absolutely right. The costs are dropping dramatically. And overall, the system was $300. So in the future, you can imagine this dropping even more and more and more as LiDAR becomes even more prevalent, which provides, I think, more incentive to see if we can, kind of find that compromise between accuracy and time. And that's only going to get better, especially as processing moves forward. So this was very fascinating to me because we're seeing what the potential is here on a low cost, and it's just going to get better in the future.
You know, and I wondered along those lines too, and this is not my area. I haven't had to think about these kind of things, but you know, Devin mentioned that one of the limitations was really just having the USB in the loop to try and collect the data seemed to be a drag on some of the time, the lag time for that. So are there other data collection or data storage methods that are available or might be getting better that would improve on that as well?
I looked into a couple things, but basically it was the limitation of the Arduino coding, where the data had to be stored somewhere, and that was going to take up a little more time than the rest of the code.
Mm-hmm.
I did try to simplify the code as much as possible, trying to save on processing time.
Mm-hmm.
But in the end, if you want to save data, it's going to take a little bit of time to save data.
Sure, sure. Well, and that's, yeah, there's only so far you can go with, limiting your code. At some point, you have to use the hardware. All right, are there any other questions? Going once, going twice, final call. Okay. Well, thank you for an informative talk. I liked your slides. I liked the presentation you gave. You guys have done a lot of work, and it's pretty clear that what you've got is a pretty neat system that, especially compared to the $6,000 to $100,000 cost that other commercial systems have, it seems like there's real potential for once you have this system where it can be field hardened, you're going to have, it seems like a lot of new uses are going to open up for this kind of technology. So keep up the good work. If anybody has any final questions after we leave, possibly the easiest way to contact them, you can see that both of them have their email addresses there on that final slide. And so feel free to jot that down or take a picture of it or screen capture, and I'm sure they'd be happy to answer your questions later. With that, we will wrap this up and we're adjourned. Thank you everyone for attending.
All right, thank you. And thank you, Devin.
Yes, thank you.
Thank you for Matthew.